Welcome to another new series on gear technology. In this series we'll be looking at how gears can be used to increase or reduce the speed of the load. Also, we will be looking at how gears are used to change the direction of rotation as per the arrangement of the gears. In the same vein, we will also be looking at how speed are converted to torque. And finally, we will be looking at how special motion can be generated using gears with special shapes. So without any further ado, let's get started. Before we dive in, it is important for us to have a deeper understanding of how gear works. Gears are a fundamental part of any mechanism, which is because of their ability to transfer motion, force, and torque between different components. And that said, there is a huge number of different types of gears. The types depend on what task they are to perform. Changing the speed or force of rotation, changing the axis of rotation, transferring power between a motor and other moving elements, etc.
And it is on this note that gears are known to be operated in mated pairs, in which the gears mesh their teeth with the teeth of another corresponding gear or tooth component. This arrangement prevents slippage during the transmission process. Each gear or tooth component is attached to a machine shaft or base component. Therefore, when the driving gear provides the initial rotational input, the driven gear tooth will be impacted by the driving gear, and as such, the driven gear will begin to rotate too. But the rotation will be in opposite direction.
I know that you might want to ask if there might be a way in which the axial rotation of the driven gear can be in the same direction as the driver. One of the ways in which this can be achieved is through the use of an idler gear. This is a clever and ingenious way of doing things, which is because when the teeth of two gears are brought in close contact, the gears of the driven are always in an opposite direction. So when these gears are further brought in close contact with the first gears here, then the same axial rotation can now be achieved at the driven gears.
Also, just by changing the size of the gear, the speed of the driven can also be changed as a result of the varying gear size. This equates to the time of travel between both gears, and the location of the larger gears will determine whether we are having a speed reducer or speed increaser gears arrangement.
Which is because at the end, we are looking at the complete rotation of the shaft. And when we look at it from another point of view, the shaft with a small gear size completes its axial rotation than the shaft with a larger gear size. This is a factor that influences the generated speed on the driven end. And it is on these bases that gears come in ratio, and this ratio is based on the calculation of the teeth of the two gears. That is, if the driven has 85 teeth and the driver has 27 teeth, then the ratio between both is 3.14 to 1. This ratio will determine the speed of the load.
Now, in order to fully understand what we are talking about, let's connect a motion sensing device at the driven end. This device is usually preferably called an encoder. Now when we turn the side with the larger size gear, the speed we got is around 80 rpm. Now when the same step is repeated with the side with a smaller gear size and when the applied force is constant, The speed generated from this end is around 25 rpm. This explains why the speed at driven end has a relation with the gear size.
Now in terms of torque, it is important to note that the speed reducer gears arrangement produces a higher torque on the driven side, while the speed increaser gears arrangement produces a less torque on the load side.
Of course, this is because of the gear arrangement. The torque produces is in relation to the generated speed. And that said, the reason why gears with reduced size produce more torque than gears of larger size is because the force acting on the shaft is a little bit closer to the teeth, and with the above ratio, and in our case here, 3 or more revolutions in order for the driven gears to make a complete revolution. And when we factor all these, then more torque will be produced. However, reverse is the case with gear with larger size and more speed at the driven. It can be seen that the force acting on the teeth is further away, and with these lesser force is applied to the driven. Although the speed is on the increase in this configuration, the generated torque will be less.
And it is on this basis that gears can be categorized on the basis of their teeth design and contacts. For examples but not limited to, we have spur gears, helical gears, gear racks, bevel gears, mitre gears, worm gears, screw gears, and internal gears. These are the most common teeth design we have in today's market.
Now that we have known how gears can be manipulated to get our desired operating speed, the direction of rotation, and the desired torque, now, there is a need to look at the type of mechanical movement that we have. There are 4 common types of mechanical movement in industries today. These movements are linear motion, rotary motion, reciprocating motion, and oscillating motion. And it is important to note that this motion depends on the shape of the gears.
So manipulating the shape of the gears in a certain way and when arranged in a way, this will determine the type of rotation that we will be getting at the driven end. With that said, in the coming series, we will be looking at the type of gearboxes that we have today in our industries, which are spur gearboxes, helical gearboxes, bevel gearboxes, worm gearboxes, planetary gearboxes, and herringbone gearboxes. I hope you have learned something new today. See you at the next one.